Welcome back, everyone, to the final session of the day. Today, we will have the first Gong show. And before we begin, let me remind everyone that each speaker has 5 minutes and that there will be a sharp cutoff. So after 5 minutes, we will cut the audio and move to the next speaker. And we also ask you to save all of your questions to the end of the Gong show because we will have a discussion session then. Okay, so let us begin. The first speaker is Mrityunjay Verma from the University of Southampton, who will tell us about higher spins and gyromagnetic couplings.
So let me begin by thanking the organizers for giving me this opportunity to talk about this work. So this is a work done with Raffaele Marotta and Massimo Tarona. So I shall be talking about the interaction of massive higher spin fields with the U1 gauge fields. At the lowest derivative order, we can write two types of coupling between the gauge fields and the massive field. So first is the minimal coupling, which introduces the charge of the field. And the second is the non-minimal coupling, which is proportional to field strength. So here you can see, so first term, so that is proportional to charge Q, and the second term, which is proportional to a constant alpha. So the field phi in this expression can have an arbitrary index structure, which is characterized by a generic Young tabular. And now one can define the gyromagnetic factor as a ratio of these two coefficients, factors, which alpha by Q. And tree level unitarity in field theory and open string theory implies the value of G to be 1. And for the Kaluza line BPS states having zero winding, the value of G turns out to be 1. So in this work, we analyze the G factor for massive string excitations with respect to U1 gauge fields, which arise from both the graviton and Kolb-Raymond fields upon compactification. Now in 4 dimension, all the fields can be classified as totally symmetric fields up to duality transformations, so that the Young tabular structure has only one row. And this implies that there is a unique non-minimal electromagnetic coupling in 4 dimension and hence a single gyromagnetic coupling. However, in higher dimension, this is not the case. There are in general mixed symmetry fields and hence there can be more than one non-minimal coupling. To characterize these couplings, it is efficient to introduce a generating function in terms of an auxiliary vector variable ui. So for example, for a completely symmetric state, one can write like this. So in terms of this generating function, the non-minimal coupling can be introduced, can be expressed in this way, where Si mu nu has this structure and the inner product in this expression is defined in this way. So this gives a basis of gyromagnetic ratios. And for each row in a Young tabular diagram, we have one such factor and one such gyromagnetic coupling. So now in analyzing the 3-point interaction between the gauge fields and say 2 massive fields, which is needed for reading of the gyromagnetic coupling, one encounters a string product such as this, where epsilon, this E, curly E denotes a generic string state. SL and SR are the left and right contribution to spin angular momentum, and X, Y are some constant. So the G factor can be extracted by expressing this inner product in terms of generating function inner product using say Wigner-Eckart theorem. So to see where does this arise, we focus on higher spin fields coming from compactification and use the Hamiltonian formalism. More specifically, we consider the bosonic and superstring theories in the background of metric and Kolb-Raymond fields compactified on a generic torus TD. So this compactification gives rise to massless U1 gauge field. So GMN metric gives rise to vector field A mu A, and Kolb-Raymond field gives rise to gauge field B mu A. So the expectation value of Hamiltonian, which describes the interaction between the gauge field and wall sheet fields for a generic string state in bosonic type 2 and heterotic string, it takes a same uniform structure. And it is this expression where this SL spin and angular momentum correspond to that specific theory. And this QA and curly QA, they correspond to Kaluza line and winding charges. And similar expression can also be obtained by explicitly evaluating the appropriate 3-point string amplitudes. So from this expression, we can read off the gyromagnetic coupling. So to do this, we need to slightly do some work. So for states with PL equal to plus minus PR. So PL and PR are the left and right internal quantum numbers. So for this, we obtain the well-known result G equal to 1. But more non-trivial examples correspond to states with non-zero winding. So we consider two examples from first trajectory of a string spectrum. So if you consider totally symmetric fields, then for such a state, the relation between the string inner product and this generating function inner product is this. And this allows us to read off the this gyromagnetic coupling. This alpha will be used in reading gyromagnetic coupling. And similarly for mixed symmetry fields with having two row in the Young tableau structure, we have this relation. And using this by comparing with the expression of Hamiltonian I wrote earlier, we can read off the G factor in this manner. So for symmetric field, it is this, and for mixed symmetry, it is this. So thank you.
Very good. Thank you very much, Ritunjai. And we'll save the questions to the end of the Gong show. So now the next speaker, Kashyap Sitender. Can you share your screen?
It shows that I cannot start screen share unless the other speaker is. Mrityunjay, can you stop sharing yours?
Yeah, I have stopped sharing.
Okay, yeah. Yes, mine now. Hello?
Yeah.
Hello?
You still cannot share the screen?
Audible?
Yeah, we can hear you.
So shall I start?
Sure. Let me reset the clock. Okay, so our second speaker is Kashyap Sitender from the University of Physics, Bhubaneswar, who will tell us about 2.3 amplitudes in the pure Spinor superstring.
Sorry, but I can't see the slide.
Oh.
Yeah.
Do we have the? Can you share your screen?
Oh, it's not visible?
It's not visible.
Not yet.
Okay, let me do it again.
Make sure you share the same, the correct file.
Yeah. Is it visible now?
Yes.
Okay, so okay.
Please go ahead.
Okay. So thank you organizers for giving me this opportunity to present my work on 2.3 amplitudes in the pure Spinor formalism of superstrings. So this is based on this work. Now to begin with, let us recall the history of 2-point function in string theory, which were traditionally assumed to vanish. Let us see why. Let us recall the amplitude prescription for 3 amplitudes, which are given by this expression. Here phi are the fields, external fields, and G is the voltage metric, and V is the volume of the reparameterization group, and Vi are the vertex operators. Now, when there are more than 2 vertex operators, using the Faddeev-Popov gauge fixing, we can get rid of the gauge volume in the denominator, and this volume includes those of the conformal Killing vectors. Now, for 2 conformal Killing vectors, one of the CKV remains unfixed, and the resulting path integral is of the form n by infinity. So far, n was assumed to be finite, implying that the 2-point function vanishes. But recently it was shown that n is infinite as well, and the corresponding infinite by infinite expression was shown to be well defined, and it gives the standard 2-point amplitudes in the QFTs, which is given by this expression. This, however, was done for the bosonic strings. We extend the proof to superstrings. Let us quickly recall some essentials of pure Spinor formalism, which is given by this action. Here, x and theta form n equal to 1 superspace in 10 dimensions, while lambda is the pure Spinor, with W alpha being its conjugate momentum field. The amplitude prescription for n-point strings is given at tree level by this expression, which involves 3 unintegrated vertex operators Vi and n-3 integrated vertex operators Us. Any non-vanishing correlator contains 3 lambda and 5 thetas, and this is the only non-zero correlators. Now, if Vi contains Vi, the unintegrated vertex operators, contain just one lambda, and hence a naive application of this prescription for 2 points will give 0 results. But this is historically fine. However, this is in conflict with the result I just now mentioned. Now, so why does it happen? The point is that the amplitude prescription given earlier implicitly assumed that we have fixed all the CKBs by fixing position of kappa of the vertex operators, where kappa is the number of CKBs. On a disk or a sphere, we have 3 CKBs. Thus, the earlier amplitude was valid for 3 or more external strings. So for the amplitude, so far the amplitude prescription in pure spinor formalism has not been derived from a worldsheet reparameterization invariant action. Consequently, it is not possible for us to give a first principle derivation of the 2-point amplitudes which do not vanish. So what we'll do in the following is to give a prescription, and that will be justified by the fact that it reproduces the correct result. So while is when I integral q is the real unconstrained. Now, next what we do is we calculate this correlation function, and that involves the following steps. First, we use the on-shell condition, momentum conservation, and then finally we perform the Q integral. And after doing all of this, we find this particular result. But this is identical to the 2-point function that I in the field theory, which I mentioned earlier. And this details can be found in this paper. Now, thus we see that A above is the correct 2-point function. So this explicitly verifies that the 2-point amplitudes are finite in superstrings as well, because pure spinor formalism is for superstrings. Now let me, in the remaining time, give some features of and applications of V0. The various ingredients like lambda, gamma, 0, theta, these go in producing out the K0 factors. Q integral gets rid of the energy delta function. V0 itself can be used to fix the remaining CKB. Also, one important feature is that V0 is a BRST, mostly BRST exact operator. That is to say, its integrand is BRST exact for Q not equal to 0. This prescription can be used finally to fix the overall normalization constant that are left undetermined by 2-point function. Thank you. Thank you. Hello.
Louis, you are muted.
I am sorry. Thank you very much, Sitender. Sorry, thank you, Kashyap. We now have the next speaker, who is Wanda Lin from Peking University.
Can you hear me?
We can hear you, but
I need to share my screen.
right.
Yes, I can do it now.
Okay.
So can you see the slides?
We can now see it.
Yeah, so I will start now.
Okay. Please go ahead.
Hello, everyone. I'm Guanda Lin from Peking University. And today I'm going to talk about some of our recent work about the non-planar form factors from the on-shell methods. You can see the following paper for more details. So what are form factors? Well, form factors, they are matrix elements between the on-shell asymptotic states and the off-shell local operators, can be expressed in the following formula. Since they contain both the on-shell quantities and the off-shell quantities, they are useful bridges to connect the on-shell world and the off-shell world. So there are many important motivations for us to studying form factors. So first, form factors can be used to reveal the IR and UV structure in quantum field theory. For example, recently, the for-loop non-planar cusp anomalous dimension can be obtained by calculating some Sudoku form factors. And also, form factors can be used to calculate some real process. For example, the Higgs to ground amplitudes in the large top mass limit. Another point is that form factors are ideal test grounds for generalizing the methods and structures developed for the on-shell methods, amplitudes. For example, the unitarity methods and the color kinetics duality structure, which will be our concentration in later. So for simplicity, we will only focus on the n=4 super Yang-Mills theory. And in this theory, there are two types of diagrams. The first is the planar diagrams, and the second is the non-planar diagrams. Well, the planar case is actually beautiful and well understood. It's partly because that the color part and the kinematics part, well, they are decoupled in the planar case. So this will lead to some enhanced symmetry, such as integrability. But the non-planar case, well, they will be more complicated. The color and the kinematics part, well, they are coupled. But the non-planar contribution is also useful because in real life QCD, NC is 3, so the non-planar contribution is not small. And to understand the relationship between the color and kinematics, and to understand how the planar symmetries are preserved or broken in the non-planar context, we really need the non-planar contribution. So how can we calculate them? The first method is the unitarity method. Well, the spirit of unitarity is to construct some complicated amplitudes or form factors with simple building blocks. For example, one can calculate some loop level amplitudes just by using simple tree level amplitudes. Well, the unitarity is it focuses mainly on the kinematics part. So how do we deal with the problem of the color part? Well, we use the color decomposition. By combining unitarity and color decomposition, the color part and the kinematics part, well, they are actually decoupled and can be dealt with separately, as is shown in the following figure. So the color part can be decoupled by the color decomposition in the upper part, and the lower part is the non-planar cuts to calculate the kinematics part. So another method we use is the color kinetics duality. In this strategy, well, we actually do not try to decouple the color and kinetics part. We try to make use of the entanglement between these two parts because we have a conjecture of CK duality, which means that the color Jacobi relations can also be satisfied by the kinematics numerators. These are called dual Jacobi relations. And using these dual Jacobi relations, one can get all the kinematics numerators from just a few master numerators. For example, in our two-loop construction, only 2 master numerators are needed to calculate all other numerators. And these two, as you can see, is extremely simple. So this result covers minimal form factors of BPS operators with arbitrarily high length, which means that you can contain many scalar fields in the operator. And it's also worth to mention that similar constructions also work for higher loops, which will be our concentration in the future work. So in summary, we apply and modify the unitarity and CK duality to efficiently calculate the full color form factors. And these results can be used to obtain the full color L structure or some Higgs amplitudes. So in future work, well, we will focus on the higher loop construction, but it's also interesting to consider some non-BPS operators for CK duality, and our method should also work for the general series with or without supersymmetry. So that's all what I want to say, and thank you all for listening.
Great, thank you very much, Wanda. So now we have the next speaker, who is Yui Hayashi from Chiba University, who will tell us about complex poles of QCD propagators and their interpretation.
Thank you for the introduction. Can you hear me?
We can hear you, but we cannot see the slides yet.
Okay. I'll share now. Can you see the slide?
Yes, now we can see it. Yeah, very good. Please go ahead.
Hello, I'm Yui Hayashi from Chiba University. I'm glad to talk here, and I'd like to thank the organizers for this opportunity. First of all, the analytic structure of a propagator provides information on state space structure not orthogonal to this state corresponding to the field. For example, the Chelan-Riemann spectral representation indicates that singularities in the complex K-squared plane correspond to states not orthogonal to this state. So we can probe states involving the field by looking into the propagator. Our big goal is to understand the color confinement mechanism. So to this end, it could be helpful to see the state space structure involving the confined field. Therefore, we investigate the analytic structure of mainly the gluon propagator in the Landau gauge, which is well studied in many numerical and analytical works. To investigate analytic structure of the propagators, one has to assume analytic form of such propagators. For this purpose, we use the massive Yang-Mills model for modeling propagators, modeling the QCD propagators. The massive Yang-Mills model consists of the usual Landau gauge Faddeev-Popov Lagrangian and a naive gluon mass term. The introduction of such an effective gluon mass term can be understood as the most tractable and infrared relevant way to take into account some non-perturbative effect, for example, the Gribov copies or dimension 2 gluon condensate, and so on. By choosing the parameters, the gluon and ghost propagators of this model present striking agreement with lattice result in the one-loop level. This line is a one-loop gluon propagator of this model, and these small dots with error bars are the lattice result of the SU3 pure Yang-Mills theory. So although the massive Yang-Mills model itself is not a consistent theory due to the lack of the nilpotent BRST symmetry, this model can be used for modeling the propagator because of these motivations and this striking agreement. Thus, we use the one-loop propagators of this model to study analytic structures of QCD propagators. As a result, near the best fit parameters to the lattice result, both gluon and quark propagators have one pair of complex conjugate poles in the complex k-squared plane. And such complex poles invalidate the Chen-Lehmann spectral representation. Moreover, not only our works, but also recent analyses of independent approaches, for example, Padde from lattice data or solving Dyson-Schwinger equation in complex k-squared plane and so on, consistently suggest that gluon propagator has some complex singularity. So it would be a good time to consider formal aspects of complex singularities. Since we have fitted the propagator to the lattice results, we shall begin with the Euclidean propagator, namely the Schwinger function. So we reconstruct the White-Arm function from the Schwinger function with complex singularities by this relation. Here are analytic properties of them in the presence of complex singularities. The first two properties are usual, but the last two properties are different from those of the standard case. First, the White-Arm function is holomorphic in the tube. Second, it has boundary value as a distribution, which satisfies Lorentz symmetry and locality. Third, while the boundary value is a distribution, it is not a temporal distribution. So the White-Arm function is beyond polynomial growth. Fourth, the complex singularities violate the reflection positivity of the Schwinger function. Although these two properties seems pathological, but the reconstructed White-Arm function from complex singularity can be realized in a state space with an indefinite metric, which is very common in covariant gauges. So in particular, complex singularities correspond to pairs of zero norm states, which should be confined by some confinement mechanism. So in a physical state space, there will be no problem. This is the summary. So what I want to say is complex singularities might appear in the quark and gluon propagators and can be interpreted as confined states. That's all. Thank you for listening.
Great. Thank you very much, Yui. Now we'll move on to the next speaker, who is Sayali Bhatkar from the Indian Institute of Science, Education and Research, Pune, who will tell us about word identity for one-loop subphoton theorem.
Hello. So is my screen visible?
Yes, we can see your screen.
Okay, thank you. Thank you for this chance. So the title of my talk is Word Identity for Loop Level Subphoton Theorem. This is a brief overview of my talk. Okay, so let us start with what are asymptotic conservation laws. In classical theory, this conservation laws take following form. The future charge is defined at scry plus minus. Scry plus minus is the u goes to minus infinity sphere of the future null infinity. The past charge is defined at scry minus plus, where scry minus plus is the v goes to plus infinity sphere of the past null infinity. So the conservation law tells us that these charges are conserved in this asymptotic sense. Now at the quantum level, the S matrix has to satisfy a body identity of this form. Q plus is the future charge and Q minus is the past charge that we described earlier. And it has been demonstrated that these body identities are equivalent to soft theory. The asymptotic conservation laws in the classical theory are equivalent to the quantum soft theorems. And this was first proved by Hay, Mitra, Porfiridis, Strominger in a particular case, and it has been later on extended to many other cases. Now in the soft limit, scattering amplitude, it takes following form. The leading order term goes like 1 over the soft energy. This mode is universal, and this is what is called as the leading soft photon theorem. And in 2018, Sahu and Singh derived the subleading soft photon theorem for loop amplitudes. This term goes like log omega. They showed that S log is universal. Okay. Now the question that we want to ask is this: is the log omega soft photon theorem also related to a new asymptotic conservation law? Okay, so we'll work in massless scalar cumulative, and the coefficient of the log omega term, it takes following form. Okay, so let us first note that the log omega mode that we described earlier, it arises due to long range electromagnetic forces acting on the scattering particles. So we will study the effect of long range force on the massless scalar field. This is the equation of motion of the massless scalar field. This is the free part of the equation of motion. And here on the right hand side, we have considered the effect of the coupling of the field to U1 gauge field. This is the dominant field, the leading order term at large r at the asymptotics. And so this is the 1 by r potential that is filled by the phi field, the scalar field. Now we can write down the solution to this equation. It takes following form. B and D dagger represent the free scalar data, and we see that the effect of the electromagnetic coupling is to introduce a logarithmic dressing of the free data, of the free scalar. Okay. Now we can show that the effect of this dressing is a new logarithmic term in the U1 current. The U1 current gets modified, and there is a new logarithmic term which depends on the dressing AR1. Now we will find the radiative field that is generated by above current, taking into account this correction. And we show that at future null infinity, there is a log U mode in the field strength. Similarly, at the past null infinity, there is a log R mode, and these logarithmic modes are related to the long range interactions present between the scattering particles. And we show that these modes obey a asymptotic conservation law of this form. Okay, so this is a new asymptotic conservation law that we derived. Now the next step is to relate this charge to the log omega soft photon theorem that we described earlier. So we start with this conservation law, and we can define a charge using the using above mode, and y is an arbitrary parameter, and next we will quantize this charge. Okay. Now the charge is made up of two parts. One is the soft part and the other is the hard part. The soft part of the charge leads to insertion of a soft photon in the word identity. In particular, it leads to insertion of the log omega mode. The hard part of the charge takes following form. It is proportional to AR1. So we recall that AR1 is the dressing of the massless scalar field under electromagnetic force. It is important to note that AR1 is 0 classically, and the log omega mode vanishes classically. So we'll calculate AR1 mode in the quantum theory and substitute in this expression, so that the Q hard operator acts on the states and it produces the soft factor S log. Okay, so this is the final form of the word identity, and this reproduces the Sahu-Sen soft photon theorem, the log omega soft photon theorem. So the conclusion is that the new asymptotic conservation law that we described is really equivalent to the log omega soft photon theorem. Okay. So at one loop level also we have a one loop exact log omega soft photon theorem, and the memory was described by Ladda and Sen. And the third corner, that is the asymptotic symmetry underlying this odd-photon theorem, is still in progress. As a first step, we derived the asymptotic conservation law that is related to our photon theorem, but the underlying symmetry, this charges, is not clear yet. Okay, so thank you all.
All right, thank you very much, Sayali. So now we prepare for the next speaker, who is Takuya Yoda from Kyoto University, who will tell us about quantum phase transitions in three-dimensional SQED and Lefschetz symbol analysis.
Thank you. Can you see my slides?
Yes, we can see them.
Okay, thank you. So let me start and thank the organizers. So I'm gonna talk about quantum phase transition in three-dimensional supersymmetric QED and the Lefschetz symbol analysis. So let me start from the motivations. Non-perturbative physics is a long-standing problem. One of the promising approaches to the problem is resurgence. It is an approach to non-perturbative physics from a perturbation theory. It might sound like a contradiction, but actually it is expected to be possible by following this route. There are two keywords: Boyle reformation technique and the Lefschetz symbol analysis. So our goal is to support this scenario in a three-dimensional supersymmetric QED. So let me introduce this concept. Resurgence is a conjecture. In a wide range of QFTs, it is expected that non-perturbative physics is encoded in a perturbation theory. What do I mean by this? Let me start from the Boyle summation technique. Let us consider a perturbative series like this, and typically the coefficient of this series can grow factorially, but we replace this factorial with the gamma function integral expression and exchange the order of the integral and the infinite sum, and we obtain this finite result. One possible obstruction to this procedure is with a singularity on the positive real axis. It is called the Boyle singularity, and this is called the Boyle summation. The Boyle summation gives an ambiguity due to the dependence on this integration contour. This is because the existence of Boyle singularity. The ambiguity typically has a form like this. It depends non-perturbatively on coupling Z. What's the meaning? What's the physical meaning of this? The answer resides in the Lefschetz symbol analysis. Consider a path integral of complexified theory. The Lefschetz symbol the steepest descent of the theory, like this. If we if we slightly change the parameters, the timbers, the topology of the timbers might change. In this figure, two saddles contribute to the path integral, and in the bottom one, only the blue saddle contributes the path integral. Due to such a dependence on the topology, we have ambiguity, which has a typical form like this. And resurgence claims that these two types of ambiguities are exactly the same with the sign flipped. And this ambiguity cancel in the theory. In that sense, we can say that this perturbation theory knows the non-perturbative effects, like this. So this is the idea of resurgence. Our final goal is to support such a method of resurgence to describe non-perturbative physics, such as phase transitions. For this purpose, we consider this model, three-dimensional n equal 4 U1 through decay theory, coupled with 2n hypermultiples with charge 1. we introduce Fi parameter eta and the paper mass m, and we consider larger framework expansion. And we find that there is a second order phase transition in this theory. Our result shows that resurgence actually works to describe this phase transition. More specifically, we can say that the quantum phase transitions interpreted in terms of Lipschitz symbols and the border plane structure property correspond to this symbol structure. The important point is that two phases are distinguished by Stokes phenomena, and the order of phase transition determined by how shadows collide, etc. So if you are interested in these topics, so please feel free to contact us. Thank you.
Great. Thank you very much, Takuya. We'll now move on to the next speaker, whose motion Karkairan from the Center for Theoretical Physics of the Universe, who will tell us about Yukawa couplings computations for T-branes.
Yeah, thank you very much. Just let me share my. Okay. Can you see my slide?
Yeah.
Okay, so just let me go to the screen. Okay, can you see it now?
Yes.
Okay. Thank you very much. First of all, thank you for letting me give a talk here. And I want to talk about the Yukawa textures coming from the heterotic string compactification and their translation in the F-theory model. So first of all, consider a Cavli compactification of a perturbative heterotic string to 4D with a vector bundle over that. Then in these cases, the Yukawa couplings in the effective 4D theory are coming from superpotential terms in 10D of this form, roughly. So here, for example, A is just the background gauge field leaving over the Cosmology, and omega is just a holomorphic top form. And to see whether the Yukawa couplings are actually zero or not, we should check the following maps between the cohomologies. For example, here, the H1 of the V, for example, corresponds to the fluctuations of the background gauge field here, and H3 of OX is just a holomorphic top form. So to check whether these maps are actually non-zero or not is a hard calculation in general. But we know that it is shown that most of the Cavli threefolds that constructed so far are actually elliptically fibered. And over such kind of manifolds, we can use a Fourier transform to define a vector bundle. So if we satisfy some certain topological and stability conditions, we can show that the Fourier transform of V is given by the spectral data, which is a doublet S and L, where S is just a finite cover of the base B, call it a spectral cover, and L is just a line bundle over this spectral cover, or basically a rank 1 coherent sheaf. So if I let the S to be reducible, then we get a lot of options for Yukawa textures, Yukawa couplings in the heterotic model. And basically, this kind of cohomology computations is also much easier in terms of the spectral data. And because it's now in terms of a spectral cover, we can also easily translate it in terms of a local F-theory model. And because we are assuming that the spectral cover to be reducible, then we are in a T-bearing situation in the F-theory. Basically, the geometry of the F-theory doesn't determine the effective gauge group for you. You should add some additional local field theoretical data. So the point is that in this case, the Yukawa couplings are actually coming from the interaction between the modes inside the bulk and modes living over the defects inside the 7-bearing. And this is usually ignored in the F-theory models because usually people compute the triple intersection of the 7-bearings when they want to compute the Yukawa couplings. So inside the 7-bearing, we have as I said, we had a spectral data. And with that spectral data, we can construct a Higgs bundle inside the 7-bearing, which is given by a flux inside the 7-bearing given by E, and a Higgs field phi, which is a map between the E 2e times k. Basically, k is just the canonical bundle. And for example, the corresponding terms coming from the corresponding Yukawas coming from such terms inside the 7-grain model. So now, for example, consider a E6 effective theory. On the heterotic side, such kind of models are given by a SU3 vector bundle over the Calabi-Yau. Now, suppose the vector bundle is initially given by this direct sum, where V2 is just an extension of two line bundles. If this extension is basically non-generic, we can show that in some special cases, the spectral coverage actually becomes like this, becomes degenerate. And the Higgs field inside the F-theory model is actually given by this 3x3 matrix. And there are some bulk Yukawa modes that they can actually, and the Yukawa modes actually coming from the bulk modes. Now we can deform this model in two different ways. For example, if I deform V2 to a generic vector bundle, then we have to Higgs many of those Yukawa coupling, Higgs many of those zero modes by turning on this off-diagonal term. And still we have a Yukawa coupling, but they are actually coming from the interaction between bulk and defect modes. We can also turn on some open string modes, but I think I'm running out of time. But even in this case, even though the spectral coverage is the same, we have some bulk modes. We don't have bulk modes. We have some defect modes actually. So this is all. I should stop here. Thank you.
Great. Thank you very much, Motion. So we'll now move to the next speaker, who is Wang Xiaojiang from the Korea Institute for Advanced Study, who will tell us about the bottom line constraint on inflation from Swampland conjectures.
Hello, everyone. My name is Xiaojia Wang, and I'm honored to be here to share with you my two recent work with Professor Ronggen Cai on the bottom line constraint on the inflation from the Swampland conjectures. So I want to use a cartoon picture to illustrate the Swampland programs. We are standing at a solid land of the standard model particle physics cosmology, which is supported by many experimental and observational evidence. But at the meantime, we also have a landscape of string vacuums. A low energy effective theory is in the landscape. It is a UV completion into the quantum gravity. Otherwise, it is in the Swampland. And the Swampland program is a theory conjecture that could help us to distinguish the landscape from the Swampland. So this is the pictures I borrowed from the Matt Ruiz talk in Spring 2019 to give you a bird view of the current progress of the Swampland program, which is classified according to their predictivity and regularity. Much attention has been focused on these three conjectures, as well as the recently proposed trans-Planckian sensitivity conjectures, which should be somewhere over here. Since most of the Swampland conjectures are far from a rigorous proof, so I want to look at the Swampland programs from a different angle that maybe we can find a most conservative constraint on the inflation. The trans-Planckian sensitivity conjecture requires that all modes that exist have a horizon at the end of inflation should have their physical length scale larger than the Planck length scale at the beginning of the inflation. So we have a bound for the duration of the E-folding number of the inflation, inverse proportional to the Hubble scale. For instantaneous reheating history, the infinity E-folding number is 46. So the infinity Hubble scale should be smaller than the 0.02 GeV, and the tensor to scalar ratio should be smaller than the 10 to the minus 33, which is extremely small that actually rule out most of the inflation model. Okay, even for the non-instantaneous reheating history, the above constraint could be relaxed at the price of the ultra low reheating temperature. So therefore, the TCC imposed a huge challenges on the model building and fine tuning. It also put a very strong bound on the PBH mass. For a general reheating history and PBH form at radiation dominant areas, there is actually a lower bound on the PBH mass, since we have an upper bound on the inflationary Hubble scale. The final result is shown in this picture, where the gray shaded region is ruled out by TCC if the inflationary Hubble scale is larger than certain value. And furthermore, since we have an upper bound on the inflationary Hubble scale, there is an upper bound for the ruled out region, which is 125 solar mass. So this simply states that one can never rule out 100 solar mass PBH from TCC alone. So all these results are independent from the detail of the reheating history. Although not showing here, I also worked out the case of the PBH formed in the matter-dominant era before reheating, and the PBH mass has an upper bound in this case. So for given NS particle state, the gravity coupling to the gravity coupled to a scalar series would become strongly coupled above a species scale, which is this lambda s. And the number of particle states that we can include is in the effective theory before reaching the strong coupling cutoff is this number, NS. And this will give us the NS with this form. And then using either scalar weak gravity conjecture or the strong scalar weak gravity conjecture, we can induce the NS with this form. And the Hubble scale as an infrared scale should be smaller than the UV scale. So finally, we should have our refined TCC with this form. For a non-external inflation, there's a relation between the E40 number and the field excursion. And our refined TCC in this case would become like this one. The physical meaning of this bound is illuminating. For a given inflationary potential in the effective series below lambda s, the E40 number is bounded by this bound. Otherwise, the larger E40 number leads to a larger field excursion, and hence a larger number of particle states would be included to spoil down the effectiveness of original theory. So although not showing here, I also use some entropy bound to get the same result from our refined TCC. So in the end, let's look at the cosmological implication for non-external inflation. For example, the slope parameter at order -2, the inflationary scale could be realized to the God scale. And the lifetime of a DS vacuum should be bounded by the Hubble times up to a slower parameter with additional logarithmic correction. This is also derived in this paper. And the same logarithmic correction is also shown in the DS scrambling time in this paper. And furthermore, the distance conjecture seems to be weakened with the same logarithmic correction. And this also derives in this paper. So for external inflation, for example, a quadratic potential, the landscape is identified in this parameter region, and beyond which our refined TCC and the perturbativity are violated. And that's all of my talk. Thank you.
Thank you very much, Xiao Jiang. We will now move on to the next speaker, who is Hoiki Madison Liu from the University of Tokyo, who will tell us about wave functions in DS-CFT revisited, principal series, and double trace deformations.
Okay. Okay, thanks for the introduction. And can you see my slides now?
Yes, we can see.
Okay, thank you. So first of all, I want to thank for the organizers for giving me the chance to have this talk. And my talk is basically based on a paper we published last month in collaboration with Hiroshi Isono and Toshifumi Nomi. And and our motivation is mainly about our motivation is mainly about the study of the inflationary correlators, which is related to the late-time de Sitter correlators. And we extend the safety dictionary for especially heavy scalar fields. And as some of you might know, the standard safety dictionary for light scalar fields suggests that the late-time wave functions on d+1 dimensional de Sitter space is equivalent to the generating function of the DLCFT in d dimensions. And so the coefficients in the wave functions can be expressed in terms of their dual CFT correlation functions, and so could their late-time correlation functions. But if we calculate the two-point functions, for example, in the super horizon region, we find that for light scalars, this dictionary is indeed valid. But for heavy scalars, the two-point function does not follow a simple scaling rule, so it is not precisely correct for heavy scalars in the principal series. So in our work, we revisited this dictionary for heavy scalars, and we found that the quadratic term in the wave function should be interpreted as a two-point function on a cyclic RG flow, which is obtained by double trace deformations of the dual CFT. And to derive that result, we studied a theory of a free scalar with mass m on d plus 1 dimension of the zeta space with two different kinds of boundary conditions. And first, we considered the Dirichlet boundary condition on its future boundary, which is usually used in the context of inflationary universe, and it corresponds to the calculation in formalism. And if we evaluate the wave function by semi-classical approximation, we obtain the result as here, and we can see that the coefficient has a very complicated form. But if instead we employ a mixed boundary condition, which involves a time derivative here, we can see that the wave function here has a much simpler form, and its quadratic coefficient here could be explained in terms of CFT two-point functions. Therefore, we can say that this wave function could be identified with CFT generating functions. And so for heavy scalars, actually the mixed boundary conditions are the one which provide the natural identification of wave functions with generating functions of the would-be dual CFTs. And also, it is not difficult to prove that those two different wave functions are related to each other by this relation. And here, those extra terms are just an extra boundary action we have added. So if we use this relation along with the previous expression for psi m tilde here, we obtained an expression for psi d as well. And we can see that here it can be expressed in terms of a CFT action plus a double trace operator. And also the rest of it are just an irrelevant terms here. So from this expression, we can conclude that the QFTs due to psi d are obtained by double trace deformation of the CFTs due to psi m tilde. And also the corresponding RG flow is cyclic because of the pure imaginary scaling dimension. And also this is analogous to the ADS tachyon with the mass squared below the BF bound, which was studied by Morris in 2010. And at the end of our paper, we also derived the rigorous relation between the DS late-time two-point function and its dual CFT two-point function. And obviously, we can see that this formula is much more complicated than the original dictionary. So yeah, that's all. Thank you very much.
Great, thank you very much, Hoiki. So we will move on to the next speaker, who is Tsinghua from the Hong Kong University of Science and Technology, and who will tell us about non-standard primordial clocks from induced mass in alternative to inflation scenarios.
Hello, can you hear me?
Hello.
Can you see my screen?
We can see your screen, but you're not very loud.
Wait, hello?
Hello, hi.
Is it loud enough?
I think that it's fine, yes.
Okay,
Please go ahead.
Hello everyone, it's my great pleasure to give this talk. And this work is mainly based on the paper of Professor Xin Gang, Mohammad Hossein, and my supervisor, Professor Wang Yi, and also a recent paper of Yi, Yuhang, and me. So for primordial universe, there is no doubt that the inflation is the most successful theory. However, we have also come up with alternative scenarios. we usually express the scale factors A as power law functions with parameter P. So the problem is that how to distinguish them. We want to use our observation to select which theory is the theory of the early universe. So far, we have been extremely precise in some of the observations, like the size of the fluctuations. So we measure at different k corresponding to the horizon crossing time, which is conformal time. So we know the relation between the fluctuation and the conformal time. But the problem is we don't know the relation between the fluctuation and physical time. So it is difficult to know the evolution history of the universe. Here's the idea of the classical standard clock. Firstly, it's raised by Professor Xingang. He assumed that there was a heavy field falls into something like the potential and start to oscillate. The frequency of the oscillation is dominated by the mass associated with the physical time. So once we see the oscillation from the power spectrum, we know there's a function between the conformal time and the physical time. So the correlation function contains this integral. And normally, it is cancelled unless there is the resonance or a saddle point. So under the saddle point of approximation, we got the correction of the power spectrum. It's a sine function with k to the 1 over p's power. So p can indicate the types of the scenario. So for more general case, the mass is not a constant. It can couple with something like the scalar factor. So this is called the non-standard clause. Non-standard means that mass is not a constant. Maybe it's time dependent or something. So for the classical signal, it can be large enough, but we need fortune to observe this. But for the quantum fluctuation, it always exists. So we prefer the quantum clause. The quantum clause is that in the early universe, there was a heavy particle or field with mass m, and the associated fluctuation can be related to some massless particle like the inflaton with resonance. And after delta k, after the time delta t, if the universe is expanding, the wavelengths can be longer, and this heavy particle can decay into other massless particle with a resonance. And if we want to know the signal, we have to know the correlation between the long wavelength mode and the short wavelength mode. So the correlation function contains this term, the phase changing. So t here is the physical time. And because of the resonance, t has the relation with the k over a. So it can be expressed as a log function with k. That is the quantum signal of the inflation. So finally, we arrived at our title, non-standard quantum clocks. In our paper, we consider two simple cases. The effective mass is time dependent. It's strongly time dependent. It can be by the Ricci curvature, or it can come from the nonlinear corrections under this potential. Both of the results is that the effective mass is proportional to the Hubble constant, but it's not the constant, it's strongly time dependent. So the signal will be like this. So we can see that the oscillation term is the same as the inflation case of the standard clock, is e to the log k. This part are the same. So fortunately, we can still distinguish these two signals by the prefactor. We can see that for inflation, the prefactor is less than 0. So the signal will decrease with k1. But for alternatives, p is less than 1. So the prefactor is larger than 0. So it increases with the k1. That is the difference. So for the conclusion, if we find the quantum clock signals, the clock signal can be a good method to select the theory of the primordial universe. And also, if you find other nice non-standard clocks signals, this flow chart will be more complicated. Thank you.
Great, thank you, Tsun. We'll now have Akhil Sivakumar from ICTS Bangalore, who will tell us about towards fluctuating hydrodynamics from holography.
Hi, am I audible?
Hi, we can hear you.
Okay. So can you see my screen too?
Yes, it works fine. Please go ahead.
Okay. Okay. So thank you for this opportunity to speak at the school. I will be talking about fluctuating hydrodynamics from holography, and these are my collaborators, and this is the ID for the paper on which this talk is based on. So let me start. So our aim is to derive the open effective action for long distance or hydrodynamic modes of a planar holographic CFT in d dimensions. And typically hydrodynamic modes are long distance modes like conserved currents and Goldstone modes, etc. And we will be thinking about conserved currents mainly, and in particular we will specialize to the diffusive sector of conserved currents. That is, we'll try to write effective actions for the diffusion of say U1 charges and energy, momentum, density, etc. In the CFT, and in particular in transverse momentum diffusion, which is due to viscosity of the holographic fluid. And we will approach this problem completely from the bulk side of the holography. That is, we will be studying gauge fields in the bulk, where the diffusion of U1 charge is dual to Maxwell field perturbations, and energy momentum modes of the CFT are dual to metric perturbations in the ADS. So we have two tasks at hand. And first task is we need to separate out hydrodynamic modes from fast or non-hydrodynamic modes. And to do that, we can effectively do that via SO-D-2 plane wave decomposition of the boundary fields, where the slow hydrodynamic modes are given by scalar sector of Maxwell perturbations and the vector and scalar sectors of metric perturbations. And the fast modes are given by vector sector of Maxwell perturbations and the tensor sector of metric perturbations. So our second task is to trace out the fast modes and write an open effective action for the reduced density matrix of slow or hydrodynamic modes. And such an open effective action is called a Schwinger-Keldysh effective action, which governs the evolution of not just states, but evolution of density metrics. So since we are looking at density metrics of CFT modes, we have both Ket and Bra copies of the boundary CFT. And therefore, the dual geometry is two copies of ADS black planes glued along their horizons. And this is a prescription which is given in detail in our paper. The desired SK effective action is then derived by standard ADS CFT dictionary, but applied to this double geometry, where the two boundaries of the geometry correspond to a Ket and Bra Hilbert spaces of the evolution of CFT density matrix. And the Schwinger-Keldysh action for all diffusive current modes are mapped to that of a Wilsonian effective scalar field we call phi m, parameterized by a number m. And for example, the charge U1 charges and momentum diffusion corresponds to m equal to 3 minus t and 1 minus t respectively. And then the conserved currents are derived from the effective Wilsonian scalar I mentioned by some schematic relations like this, which suggests that the conserved currents are always conserved in the formalism we develop here, and the fluctuating action, or the Schwinger-Keldysh effective action for the effective scalar phi m describes how the microscopic fluctuations of fast modes, which we integrated out, stochastically drive the hydrodynamic effective field phi m, and in turn the currents, charge density and charge currents derived from it. Thank you.
Great, thank you very much, Aki. Let's now move on to our final speaker, who is A. Navina Kumara from the National Institute of Technology, Karnataka, who will tell us about null geodesics and thermodynamic phase transition of regular ADS black holes.
Hello, am I audible?
Yes, we can hear you. Please go ahead.
At the outset, I would like to thank the organizer for giving this opportunity. So I'll be talking about the null geodesics and thermodynamic phase transition of regular radius black holes based on the work which is prescribed here. So all of us know that in black hole thermodynamics, we can map this mass, surface gravity and horizon area of the black hole to the energy, temperature and entropy. And using that, we can write the first law of thermodynamics, which looks exactly like the first law of thermodynamics in the conventional approach. But there is a difference here because there is no pressure and volume term, which is missing. So where is the PDV term in first law of black hole thermodynamics? So to incorporate the pressure term, we treat the cosmological constant as a dynamical variable so that the pressure term comes here. So one of the advantage after doing this is the smart relation and the first law of thermodynamics are consistent with each other. Now, one of the spectacular outcome of doing so is the charge radius black hole behaves like van der Waals fluids. The thermodynamic properties are exactly as that of van der Waals fluid. So one can observe a first order phase transition between the small black hole and large black hole phases. And one can even calculate the mean field theory critical exponents, which exactly matches with the van der Waals case. So those studies are done for black holes with singularities. We started our work considering black holes without singularity. So in regular black hole solution, the central singularity is replaced with a de Sitter core. So it's already known that these black holes also exhibit a first order phase transition. We studied the phase structure of these regular radius black holes, in particular the Heward and Bardeen solution. So we constructed Maxwell's equal-area law to obtain the coexistence curve, which separates the small black hole and large black hole phases. We also studied the metastable states, the superheated small black hole phase and the supercooled large black hole phase, which is obtained by spinoidal curves. So once again, the phase structure is similar to van der Waals fluid. Recently, it is reported that there exists a close connection between gravity and thermodynamics for ADS black holes, which is done through the photon orbit study. So for a photon orbit is defined by these conditions, where the first derivative of effective potential equal to 0 and the second derivative is less than 0. So we know that for other cases, if the impact parameter is greater than that, then the incoming photon will be scattered, and if it is less than that, it will be absorbed. Only if this particular condition is satisfied, it forms a unstable circular orbit. So we calculated the two important parameters, that is the radius and impact parameter of this unstable circular orbit, and studied its behavior. And what we observed is it exactly behaves as that of temperature, entropy, and pressure volume curves when plotted against Hawking temperature and pressure. So this shows that the phase transition behaviors are reflected in the photon orbit parameters. We even studied the critical behaviors from these two parameters. What we did is we constructed equal area, Maxwell's equal area law for TR and TU isobars. So by studying delta R, the change in photon orbit radius and the minimum impact parameter during the phase transition, we found that these two parameters can serve as order parameter to describe the phase transition with a critical exponent of 1/2. So to summarize, what we studied is we connected the gravity side and thermodynamic side of regular black holes using null geodesics. And we studied the first order phase transition using the two important parameters, radius and critical impact parameter. And their difference during the phase transition serve as order parameter for phase transition. Thank you.